Hey there, it's Shannon MATHCHICK, and today we're talking about symmetric matrices and orthogonal diagonalization. So, symmetric matrices arise more often in applications than any other major class of matrices. The theory depends on both symmetry and orthogonality. For most matrices, you need to go through most of the diagonalization process to ascertain whether a matrix is diagonalizable. We learned about one exception, a triangular matrix, which has distinct entries on the main diagonal. Another type of matrix which is guaranteed to be diagonalizable, you guessed it, is a symmetric matrix. So, definition of symmetric matrix: a square matrix A is symmetric when it is equal to its transpose. So you would have A equal to A transpose. So let's take a look at which of these guys are symmetric. So A transpose is equal to, if I write the first row as the first column, I'll get -2, 5. And the second row as the second column, I'll get 5, 1. And that certainly is the same as A. So A is symmetric. B transpose is equal to, doing the same thing, writing the first row as the first column, second row as the second column, and third row as the third column. And yes, B equals B transpose. C is not, because it's not square, right? So it can't be. So C will not be symmetric. And let's check out D. D transpose will be 1, 2, 3, 4, 2, 7, 1, 0, 3, 1, 7, 2, and 4, 0, 2, 5. And yes, D equals D transpose. So A, B, and D are symmetric. All right, so now if we were to take a look at this next problem, and my apologies, I decided when I made the key, we're not going to do this particular problem. It just was needlessly complicated. So we are going to use this matrix. So the matrix A will be 1, 2, 2, 1. So if you recall, going through the diagonalization process, we wanted to go ahead and we need to know what I2 is to find the eigenvalues and eigenvectors. So we'll be using I2 since we have a 2 by 2 matrix. And then lambda I2 minus A is going to be equal to lambda minus 1, -2, -2 lambda minus 1. Cool so far? Excellent. So let's go ahead and do this quick. We learned how to do this in the last section, I believe. So we want to find the eigenvalues by setting the determinant of lambda I2 minus A, which was this one, and we'll set this equal to 0. So we'll get lambda minus 1, the quantity squared, minus 4 is equal to 0. And then we'll have lambda squared minus 2 lambda plus 1 minus 4 is 0, which gives us lambda squared minus 2 lambda minus 3 equals 0. That's going to factor as lambda minus 3 times lambda plus 1. We'll set that equal to 0. And then we'll have our eigenvalues. We'll say that lambda 1 is negative 1 and lambda 2 is positive 3. Groovy? And so this portion was our characteristic polynomial. And note that we have our eigenvalues here. And we learned a theorem that said that two distinct eigenvalues for a 2 by 2 matrix means that A is diagonalizable. Okay, groovy. All right, so now let's go ahead and find our eigenvectors. So when we find our first eigenvector, I'm just going to go up here and start it. So for lambda 1 equal to negative 1, negative 1 times I2 minus A will be equal to negative 2, negative 2, negative 2, and negative 2. So that would be really easy to work with. And then we'll get, we have to basically solve this equation. Negative 2, negative 2, negative 2, negative 2 times x1, x2 is equal to 0, 0. And we'll end up with, when we row reduce the first matrix, if you notice, if I add negative row 1 plus row 2 will zero out. And putting this, and then we have our equation here, the rest of our equation. And so I'll just go ahead and plug it back in this form. So negative 2x1 minus 2x2 is equal to 0. And then we will get negative 2x1 equals positive 2x2. And so x1 is equal to negative x2. So then if we take a look at our x1 vector, we will get that's equal to x1, x2, which if we let x2 equal to t, this will be t, I'll factor out the t, and we'll just get negative 1, 1. Cool so far? And that will end up being the basis, or a basis for that will be the first column of our diagonalizable matrix. Groovy? All right, going through the similar process for lambda 2. So I'm just going to go ahead and I think I have room right here. So lambda 2 was equal to 3. And so 3i2 minus the vector a is equal to, I'm looking up at our lambda i2 minus a, we'll get for this one positive 2, negative 2, negative 2, positive 2. And so solving this equation, we will get, I just need to add those together and my second line zeroes out, right? My second row. So I'll have 2, negative 2, 0, 0 times x1, x2 equals 0, 0. And that'll give us 2x1 minus 2x2 is equal to 0. And that gives us that x1 is equal to x2. So x2 will be, the vector x2 will be x1, x2, which will equal to, if we let x2 equal to t, we'll get t times 1, 1. And then using a basis for that to get p2, we'll just have 1, 1. Cool so far? Excellent. So now our matrix P, I'll write it in black here, so P is equal to P1, P2, which was negative 1, 1, and 1, 1, going as columns. And then, sorry about my dogs, and then you can check it out. You know, it's nice on Octave. If you go on to Octave, and then we'll put in the different values. So A was equal to, let's see what our original was. Well, not our original, our new and improved problem. So we had going across 1, 2, and then 2, 1, which you notice is symmetric. And then for P, we got negative 1, this is going across now, 1, and then 1, 1. Now, if I multiply P inverse, so in octave, the command would be inv parenthesis P and then times A times P. This should be diagonal with our original eigenvalues. And look at that. When we find our P inverse AP, we get a diagonal matrix with, and then to check, a diagonal matrix with our eigenvalues that we had found. So this is our result. Groovy? Okay, so next up, properties of symmetric matrices. This is also called the real spectral theorem. This is an R. And what we have is, if A is an n by n symmetric matrix, then the following properties are true. A is diagonalizable. All eigenvalues of A are real, which is awesome. If lambda is an eigenvalue of A with multiplicity k, then lambda has k linearly independent eigenvectors. That is, the eigenspace of lambda has dimension k. So the proof of this property, in this text we can only do it for a 2 by 2 symmetric matrix. So here it goes. We're going to let A equal to A, C, C, B, which you note is a symmetric matrix. And so lambda I minus A will equal to lambda minus A, negative C, lambda minus B. And so if we find the determinant of this, we're going to have lambda minus A times lambda minus B minus C squared. And if I multiply that out, I'll get, I don't need the parentheses, I'll get lambda squared minus lambda times A plus B plus AB minus C squared. Cool so far? And the discriminant will be of what we found here, of this characteristic polynomial, is going to be, so normally you have, a square, a x squared, plus bx plus c. So in this case, we're going to have, 1 times our squared expression, a plus b times our variable to the 1, and ab minus c squared is our constant. So our discriminant will be a plus b squared minus 4 times 1 times ab minus c squared. And that, in turn, will be equal to a squared plus 2ab plus b squared minus 4ab plus 4c squared. And that is, I'm going to combine these two terms here, and we'll get a squared minus 2ab plus b squared plus 4c squared, which gives me the quantity a minus b squared plus 4c squared. Now, if this expression is positive, then by the quadratic formula, the characteristic polynomial has 2 distinct real roots. Now, if it is 0, and when I'm saying it, I mean this guy here. If it's 0, then what do we have? We would have a minus b, the quantity squared, would plus 4b plus 4c squared would equal to 0. And so that means that a would have to equal to b, this is all for it to be 0, and c would have to be equal to 0. If that's the case, a is already diagonal because you would have all zeros, right? And just of note, I didn't put this in, but do you see, since the determinant is a sum of 2 squares, it's either positive or 0. All right, excellent. And that is the proof. Groovy? All right, so now this one, prove that the symmetric matrix is diagonalizable. So this one is just kind of a cool little exercise. We need to find all of the same stuff, all right? So lambda I minus A is going to equal to lambda minus A, negative A, negative A, negative A, lambda minus A, negative A, and then negative A, lambda minus A. And so if I set this equal to 0, this being the determinant of lambda I minus A, I'll get that 0 is equal to, so if I expand across, I'll just expand across the first row. And so I'll get lambda minus A times the determinant of lambda minus A, negative A, negative A, lambda minus A, and then minus negative A times the determinant of negative A, negative A, negative A, lambda minus A, and then plus negative A times the determinant of negative A, lambda minus A, negative A, negative A. And then going through all of that, we will have lambda minus A times lambda minus A, the quantity squared, minus A squared, plus A times negative A times lambda minus A squared, and then minus A times A squared. We'll have minus and minus, so we'll get plus lambda minus A times A. Cool so far? Awesome. All right, so now we will have lambda minus A, the quantity cubed, minus A squared times lambda minus A. And then we'll have minus A squared times lambda minus A, minus A cubed, minus A cubed, minus A squared times lambda minus A. So let's see if we have any like terms. So it looks like we've got this one is a like term with this and with the very last one. And then of course we've got the two A cubes. And so this will give us 0 equals lambda minus A cubed minus 3A squared times lambda minus A minus 2A cubed. Now I'm going to expand using the Pascal's triangle. And with Pascal's triangle, I'm going to think about this binomial cube as lambda plus negative a. So we're going to get 0 times 1 lambda cubed minus lambda squared a plus lambda a squared, and then minus a cubed. And then I'll distribute the 3a squared, the negative 3a squared, to lambda minus a. So I'll have minus 3 lambda a squared minus 3a cubed. And then I have my minus 2a cubed. And let me see, I think I need to change a sign on something. Yes, I'm going to have, this will be plus. And then I have a negative a cubed, a negative 2a cubed, and that positive 3a cubed zero out. And then I have 0 is equal to, when I combine like terms, I will have lambda cubed, lambda squared a, I just have the 1 lambda squared, and then lambda a squared, a positive, and then a minus 3, so minus 2 lambda a squared. And so if I factor out a lambda, I'll be left with lambda squared minus a lambda minus 2a squared, and that in turn is going to be 0 equals lambda times, we know we have a lambda squared, and we know we have 2a squared, and that should be negative. And let's see, the negative will go here, the positive will go here, since the middle term is negative. So we will get lambda is equal to 0, or lambda plus a is equal to 0, or lambda minus 2a is equal to 0. And so this would be lambda is negative a for the second, or lambda is 2a, and that gives us our 3 distinct eigenvalues. Cool, cool? So we have shown it. Okay, find the eigenvalues of the symmetric matrix. For each eigenvalue, find the dimension of the corresponding eigenspace. You will laugh. Because, let's see, I'm going to make sure, yeah, that was all we had to do, was prove that the symmetric matrix was diagonalizable. And we got 3 distinct eigenvalues. So we're good. Now, for example, for I had, let's see, oh, this one was fine, but there was another problem where I wrote the problem down wrong, and I spent so long on it, and then I finally thought to check the problem, and I wrote it down wrong. All right, so anyway, find the eigenvalues of the symmetric matrix. For each eigenvalue, find the dimension of the corresponding eigenspace. So here we go. Lambda I minus a is going to be lambda minus 2, 1, 1, 1 lambda minus 2, 1, and then 1, 1 lambda minus 2. And then finding eigenvalues, we'll have, we need to find the determinant and set it equal to 0. And so we will get 0 equals, oops, I'll just expand about that first row, and we'll have lambda minus 2 times lambda minus 2, 1, 1, lambda minus 2, minus 1 times 1, 1, 1 lambda minus 2, and then plus 1 times 1 lambda minus 2, 1, 1. So we will have lambda minus 2 times lambda minus 2, the quantity squared, minus 1, minus 1 minus quantity lambda minus 2, nope, I flipped it, sorry. That would be lambda minus 2 and then minus 1. And plus 1 minus quantity lambda minus 2. So 0 will equal lambda minus 2, the quantity cubed, minus lambda minus 2, minus another, let's see, this ends up being lambda minus 3, that quantity, and then 1 minus lambda minus 2 gives us plus 1 minus lambda plus 2, so we'll have 3 minus lambda. Okay, so working on lambda minus 2, the quantity cubed, that'll be 1 times lambda cubed, and then minus 3 times 2 times lambda squared, plus 3 times 4 times lambda, and then minus 1 times 2 cubed. And then distributing, and the other ones will have a minus lambda plus 2, minus lambda plus 3, plus 3 minus lambda. And combining, let's see what we get. We'll have lambda cubed. We'll have a negative 6 lambda squared. I think that's our only lambda squared term. And then we'll have 12 lambda minus 3 lambda is 9 lambda. And then the constants, I think, zero out. So we'll have negative 8 plus 8. So they zero out. And so then we'll get 0 equals lambda times lambda squared minus 6 lambda plus 9, which is lambda times lambda minus 3, the quantity squared. And what are we asked to find? We just need to find the dimension of the corresponding eigenspace. So for lambda 1 equals 0, the dimension of the eigenspace is going to be equal to 1. And since we have the second one with multiplicity 2, so lambda 2 equal to 3, the dimension of this eigenspace is going to be 2 by that real spectral theorem. Groovy? Okay, and we are done with that problem. So the next step is definition of an orthogonal matrix. So a square matrix P is orthogonal when it is invertible and P inverse equals P transpose. So a property of orthogonal matrices is an n by n matrix P is orthogonal if and only if its column vectors form an orthonormal set. So remember, orthonormal means that it's orthogonal and it is also normal. So we want to determine whether the matrix is orthogonal, and if it is orthogonal, show that the column vectors form an orthonormal set. All right? So we know what A equals. We know that A transpose is equal to negative 4/5, 0 3/5, going down. So I wrote the first row as the first column, second row as second column, third row as third column. So you can see that we have symmetry here. And what we want to know is A times A transpose, is that equal to I3? Because if it is, then we'll have that A inverse equals A transpose. Does that make sense? Let's check it out. So on this one, we can certainly take a look at octave. Okay, so let's enter in A. I'll do it. Let's see, we have negative 4 divided by 5, 0, 3 divided by 5, new row, 0, 1, 0, new row, and then 3/5, 0, and 4/5. And then here we're going to let B equal A transpose. Notice we get the same matrix, but that's okay. And so what we want to know is that if I take A times A transpose, which I named B, what do I get? And look, we got the identity matrix. Groovy? So, coming back, we can check that off the list. And then just to look at this kind of mathematically, if you have A times A transpose, right? And we want to know if that is equal to I3. If we multiply on the left by A inverse, then we'll get I3 times A transpose equals A inverse, and that means that A transpose will equal to A inverse. Groovy? Okay, so next up we have another theorem, Property of symmetric matrices. Let A be an n by n symmetric matrix. If lambda 1 and lambda 2 are distinct eigenvalues of A, then their corresponding eigenvectors x1 and x2 are orthogonal, which is really cool. So if the eigenvalues are distinct in a symmetric matrix, then we know that the eigenvectors are orthogonal. So the next theorem, the fundamental theorem of symmetric matrices, tells us that if A is an n by n matrix, then A is orthogonally diagonalizable. And has real eigenvalues if and only if A is symmetric. And we'll look at the proof of this one real quick. So, case 1, because it's an if and only if. We'll assume A is orthogonally diagonalizable. And I said orthogonally diagonalizable. Then there exists an orthogonal matrix P such that D equals P inverse times A times P is diagonal. Also, P inverse is equal to P transpose. So we have A is equal to P times D times P inverse, which equals to P times D times P transpose. And A transpose equals P times D times P transpose transpose, which is equal to P transpose transpose times D transpose times P transpose, and that in turn is P times D transpose times P transpose, which equals A. So that's the first case. Case 2, we have, let's see, assume A is symmetric. So what we'll have is if A sorry, I think that's my husband talking. If A has an eigenvalue lambda of multiplicity k, then A has k distinct eigenvectors which are linearly independent. Which was from, I think, that real spectral theorem. And in our little workbook, it was theorem 4.23. By using the Gram-Schmidt orthonormalization process, we use this set of k vectors to form an orthonormal basis of eigenvectors for the eigenspace. Corresponding to lambda. Then you kind of rinse and repeat, right? Then repeat this process for the remaining eigenvalues. And by theorem 4.25 in our workbook, we know that the collection is orthonormal. Now, if we let P be the matrix which consists of these n orthonormal vectors by theorem 4.24, P is an orthogonal matrix and by theorem 4.21 in this workbook, P inverse AP is diagonal. So A is orthogonally diagonalizable. That is case 2. All right, so steps for diagonalizing a symmetric matrix. Find all the eigenvalues of A. So it's the same really as any other, except you know that it will be diagonalizable. And determine the multiplicity of each. For each eigenvalue of multiplicity 1, find a unit eigenvector. That is, find any eigenvector and then normalize it. So if you only have one, you're good to go. Now for each eigenvalue of multiplicity k, find a set of k linearly independent eigenvectors. If this set is not orthonormal, we apply the Gram-Schmidt orthonormalization process. The results of steps 2 and 3 produce an orthonormal set of n eigenvectors, and then you use these eigenvectors to form the columns of P. The matrix P inverse AP, which equals also to P transpose AP, which equals D, will be diagonal. And the main entries of P are the eigenvalues of A. Groovy? Okay, so example 5, which is our last example, we will orthogonally diagonalize A. We'll find the matrix P, which will orthogonally diagonalize. Now this is the one where I made the mistake. So this bottom, the 0 in the third row, second column should not be 0. It should be a 1. Okay? Otherwise, it doesn't work very well. So then, lambda I minus A is going to equal to lambda negative 1, negative 1. Negative 1 lambda, negative 1, negative 1, negative 1 lambda. And you'll notice that it is symmetric. And then we need to find the determinant and set it equal to 0. And so I'll go ahead and expand about the first row. And we'll get lambda times determinant lambda negative 1 lambda minus negative 1 times determinant negative 1, negative 1, negative 1 lambda, and then plus negative 1 times the determinant negative 1 lambda negative 1, negative 1. So that's going to give us lambda times lambda squared minus 1 plus negative lambda minus 1 minus 1 plus lambda. And so 0 is equal to lambda cubed minus lambda, and then we'll have a negative lambda minus another lambda will be 2 lambdas, minus 2 lambdas, and then a negative 1 minus a 1 is minus 2. So this will give us lambda cubed minus 3 lambdas minus 2. And then looking at this here, you know, you can definitely graph it using your graphing calculator. I'm going to just kind of guess that negative 1 might be a 0. So I'll have 1, 0, negative 3, negative 2. And then we bring down that 1. 1 times negative 1, whoops, is negative 1. Bring that down. And then we'll get negative 1 times negative 1 is 1. And that's going to be negative 2. And negative 2 times negative 1 is positive 2. So I get a remainder of 0. So it turns out that this expression here is going to be lambda plus 1 times lambda squared minus lambda minus 2. And then we will have this is equal to lambda plus 1 and then lambda minus 2 times lambda plus 1. And so we get lambda 1 is negative 1 with multiplicity 2. I'll just say k is 2. Lambda 2 is equal to 2. And then now we need to find our eigenvectors. So here we go. For lambda 1 equal to negative 1, we'll have negative 1 times I minus A, and that is equal to, that's the matrix, so that'll equal to all negative 1s. So do you see when you row reduce this, right, you'll get negative 1s across the top and 0s for the other rows, right? And so x1 is going to be x1, x2, x3, which is equal to, so now we're taking negative x1 minus x2 minus x3 is 0, which basically, after a little algebra, gives us x1 equals negative x2 minus x3. And if we let x2 equal s and x3 equal t, we'll have x1 would be negative s minus t, x2 is s and x3 is t, and then if you separate them, you would have s times negative 1 1, 0 plus t times negative 1, 0, 1. Cool, cool? And so P1 will be negative 1, 1, 0, and P2 will be, or no, we have to, sorry, we have to use the Gram-Schmidt theorem on those guys. So here we go. Now we apply, so if we take a look at negative 1, 0, 1, and if we normalize that, the magnitude you see would be the square root of 2. So that would be negative 1 over root 2, 0, and positive 1 over root 2. So this will officially be P1. Okay, so we got our very first vector and we normalized it. Now, to get our second vector, right, we're going to basically use our first vector non-normalized, right? So you're going to use negative 1, 1, 0. From that, we'll subtract the dot product, that's the inner product space we're using, of this vector and the one before non-normalized. So the dot product of negative 1, 1, 0 with negative 1, 0, 1. We're going to divide that by the magnitude, the inner product of the first vector with itself, which will just be the square root of 2 squared. And then you multiply it by that first vector before getting the normal vector. And so that will be equal to negative 1, 1, 0 minus, we'll have 1 plus 0 plus 0, and then, so that'll just be 1/2 times 1, 0, 1, which will be negative 1 minus 1/2 is 3/2. Oh, I'm sorry, I missed a negative in this one here. So we'll have negative 1 plus 1/2 is negative 1/2, and then 1 minus 0 is 1, and 0 minus 1/2 is negative 1/2. And then do you see that the magnitude of that is going to be 2 squared plus 2 squared is 4 plus 1. So this vector is orthogonal, okay? Now we have to normalize it. So the magnitude of this is going to be the square root. So the magnitude of negative 1/2, 1, negative 1/2 is the square root of 1/4 plus 1 plus another 1/4. That gives us 2/4 plus 4/4 is 6/4. Equals root 6 over 2. So that root 6 will go to the bottom and the 2 will flip to the top. And so at the end of the day, we will have for this one negative 1 over root 6 positive 2 over root 6 and negative 1 over root 6 is our P2. Good so far? All right. And now the last one will be the easy one. So lambda 2 equal to 2. That's going to give us this, this one here. So we'll have 2, negative 1, negative 1, negative 1, 2, negative 1, and then negative 1, negative 1, 2. We're just going to use MATLAB to find our REF of this guy. And so we'll have A equals, and this is not the A from our problem, by the way. A equals 2, negative 1, negative 1, new row, negative 1, 2, negative 1, new row, and negative 1, negative 1, 2. Return. And then our REF, A, oops, I think it either auto-corrected me or I'm pretty tired. Our REF, A, gives us 1, 0, 1, 0, 1, negative 1, and then all zeros. So that gives us x1 minus x3 is 0, and then x2 minus x3 is 0. If we let x3 equal to t, x1 equals x2 equals t, and so for this one, we will have, if I factor out the t, we'll just have 1, 1, 1, right? Now to get p, I need to divide by, so p3, I need to normalize that. So we'll have 1 over root 3, 1 over root 3, and 1 over root 3. And then finally, for the end result, our matrix P that diagonalizes A is P1, which was negative 1 over root 2, 0, 1 over root 2. That was over here. P2 was over here, and we had negative 1 over root 6, 2 over root 6, negative 1 over root 6, and then P3, we had 1 over root 3, 1 over root 3, and 1 over root 3. Excellent. So a little bit of a process. You can check on your own to make sure that this, P inverse AP is diagonal. But it's a cool process. At least with a symmetric matrix, it's diagonalizable, right? All right. So now, last problem. We want to prove that if a symmetric matrix A has only one eigenvalue lambda, then A has to equal to lambda I. So suppose P inverse AP is diagonal with one eigenvalue lambda. Then A is going to equal to P times D times P inverse, which is P in the diagonal will have lambda I times P inverse, which is lambda I times P inverse, which is lambda I times I, which is lambda I. We're done. Groovy? All right, so that wraps up the last little bit that we'll be covering for this class. And I hope you have a wonderful morning, afternoon, or evening whenever you're watching the show. If you like what I'm doing, hit that subscribe button, share the video, maybe like the video, and I will talk to you soon. Bye.